frequency. So this is the line transition, hyperfine line transition with which we want to see. You have to understand that we can only probe the universe using photons. So you studied CMBR, which is again looking at the distribution of photons in the sky, and exactly the same way. I mean, this is also a line emission. So we are interested in doing some cosmology with this particular transition. So what we did last time, what we looked at last time was okay. So we saw that when the spin temperature of the gas is low, then of course you see it. You see the 21 centimeters as an absorption feature against the CMBR. So you have to understand that the CMBR photons are traveling all the way from the last scattering surface, right? So you have a last scattering surface, and the CMBR photons are free streaming from there. And in the region that it travels through, you have the gas. So whatever changes to that temperature is induced by transitions in the gas is going to manifest either as an absorption or an emission feature about on top of the same layer. Right? So what you can measure is the difference. So if the temperature of the gas, if the temperature is the same as the CMBR, so of course you don't see anything because you just see CMBR. So any detection of the 21 centimeter signal would be possible provided it is an emission or an absorption feature. And we saw that between redshifts 220, this appears as an absorption feature, and only in redshifts which are less than that 21 centimeters is seen as an emission. Okay. So when you say 21 centimeters, you of course don't see it at 21 centimeters because the frequency is redshifted. So from 1420 megahertz, it will be redshifted to some lower frequency, and you would see it you would observe it in a radio telescope by tuning the frequency of the telescope to that particular frequency. So when you are looking at, say, 300 megahertz, you are looking at certain redshift. You are looking at the emission from some redshift Z, which is 1420 by 300 minus 1. That's the redshift you are looking at. All right. So by doing this, in this way of doing it, you can actually see the entire cosmic history as a continuous evolution in Z. You can see all the Z slices, and you can see a complete evolution. So that's why this is very powerful. Unlike CMBR, which is just a surface, this gives you the 3D image of the universe, which is very important. Galaxies are in the very local universe. So galaxies formed at a much later stage when the perturbations grew to a significant degree to form collapsed structures. That was at a much later stage, and galaxies of course don't go very deep. So only a small little slice of the universe in terms of redshift binning you can probably probe using galaxies. You cannot go to Z 30, 40 because there are no galaxies there. So, but there was this intergalactic medium, there was this neutral gas which fills everything. So this is a huge repertoire of information. Alright, so the important thing is this quantity, which is actually being measured in radio observations, and it's related. Basically, you can see that this is an interplay between the spin temperature and the CMBR temperature, which of course has the redshift information. And this is the main thing, that is brightness temperature is proportional to the number of neutral hydrogens. So this is proportional to this number of hydrogen atoms. This is very crucial. The fact that there is this proportionality immediately means that you can use this TB as a tracer of your distribution of gas. So by looking at this, you are essentially mapping out this, which is very important. So we are finding an implicit way of mapping out the temperature. Through the temperature distribution of TB, we are implicitly mapping out the neutral hydrogen distribution. So now comes the important assumption that this particular neutral hydrogen distribution, which is essentially baryonic matter, actually is believed to follow the large-scale evolution of universe, which is dictated gravitationally at least by mainly dark matter, because that is the bulk constant to it. So gravitational processes, instabilities and structure formation is essentially, I mean, the collapse and everything is essentially dictated by dark matter, and the neutral hydrogen or the neutral baryonic matter is believed to trace this dark matter in some way. So we believe, at least this is a reasonable belief, that the dark matter distribution is what dictates the distribution of neutral hydrogen, and the relationship is by some sort of a proportionality. So we believe that if there is a dark matter over density delta, which we are interested in finally, because this is what leads to structure formation, and then you have distribution of something else, say neutral hydrogen, and there is a relation between them which is, well, we don't know what it is, but we can speculate, or we can actually make a conjecture that, well, wherever there is an overdensity, there we expect more baryonic infall, and so this should be essentially proportional. Now, whether this proportionality is going to be a pure linear relationship or something non-linear or something even more complicated, that we don't know in priori. So the simplest model would be where these two are just related by a constant. So we say that the neutral hydrogen distribution simply follows the dark matter distribution by a constant factor. So such a model is basically called what is known as a linear bias model. So it's just a constant bias, B, which we denote by B, and there's just this relation which is just some bias. Now, once you have at least made this assumption that they're related by something, now you can make more, put some more non-triviality into this bias function by saying that maybe if you look at various scales, this bias probably depends on scales. What it means is that it's almost reasonable to believe that at very large scales, where astrophysical processes become less important when it comes to baryonic matter, there it is probably reasonable that this just becomes a number on very large scales. Whereas on small scales, this is probably not true, and probably there is a scale dependence on this B. What it essentially means that when you look at small scales, the fluctuations are probably of the hydrogen are probably dictated by thermal and other astrophysical effects, and not directly dictated by the large-scale dark matter overdensity. Whereas on very large scales, if you look at the same thing at very large scales, you can probably assume that a constant linear bias would be a reasonable approximation. And then again, this is, of course, going to be very non-trivial when the gas distribution is actually evolving with time very rapidly. For example, during the time where universe started to get reionized, the neutral fraction, the neutral density distribution is changing very quickly. The bubbles, ionized bubbles are forming, and you have a situation where this thing is actually a function of time as well, or a function of Z. Right? But we believe that after reionization was over, the neutral hydrogen roughly remains constant. In these little clumps that hydrogen remains after reionization is over, the neutral hydrogen content is very small, but it's a constant. It no more evolves. It's over. Whatever evolution has to occur has occurred, and this neutral hydrogen fraction is a constant. So again, there bias would probably not be a function of Z. Whereas during the time reionization is taking place, this relationship would be extremely complicated because it would not only depend on scale, it would also depend on the redshift. So it is in general an unknown function. So we don't know what to do with it. Alright? But at large scales, it is reasonable always to use what is called a linear bias model. So large scales, we have a linear bias. By linear bias, I mean a bias which is just a constant, a number. And it turns out that when people do simulations, numerical simulations, and they simulate dark matter and their evolution using the dynamical equations of structure formation, and they look at the hydrodynamic properties of gas in such an universe, and they actually calculate the ratios, it turns out that this linear bias model actually works. Even if you put in hydrodynamic effects and all sorts of astrophysical processes on large scales, when you look at scales which are pretty large, such a linear bias model actually is seen to be obeyed. I mean, and it's seen, of course, you don't know how to measure this because you cannot measure this. I mean, dark matter you cannot see. But you can always simulate, and you can always look at simulations where a linear bias model is seen to be valid at last. Bias? Yeah. Yeah, so bias is a number which is of odd, yeah. It's order unity or 2, 1, 1.5, something like that. Depends. So we'll see our simulation which we have done and what this number is actually. It turns out that in the post-reionization epoch, where this gas is essentially in very clumped damped Lyman alpha systems, there this number is actually some order 2, something close to 2, is constant. Of course, you don't know what is happening at low scales, small scales, so there you have to rely very heavily on simulations or on modeling, because you don't have a theory which explains, observational things at very low scale, because this you cannot observe. That's the main problem. You cannot see the dark matter. All you can see are tracers. In this case, this tracer is neutral hydrogen, which again is measured implicitly through measurement of intensity, which has a brightness temperature. So it's like very implicit, and all you can measure is the tracer fields. So be it galaxies, be it neutral hydrogen, you can only measure these, which are believed to be tracing the underlying distribution of dark matter. So all the probes of cosmology that you have are essentially trying to probe the distribution of dark matter, but they can only do so implicitly by probing something which traces the dark matter through some bias. So this is even true for galaxy, where you have a galaxy density function, density over density, which would be denoted by delta G, and it would be related to dark matter by some bias, a galaxy bias. So again, you have the same kind of argument. On large scales, they would probably hold true. Okay, so now coming to this, I just want to go a little bit deeper into this tau. So this tau, which I call the optical depth, is essentially related to the absorption of the CMBR as the CMBR passes through the neutral hydrogen cloud. And I'll just go through a little bit of calculation to show how this is essentially related to NH. So let's just do that. So this tau, which measures the interaction of a photon as it passes through the gas, is essentially, as I stated last time, is just alpha dl, where you have some dl, this is your line of sight, and some gas is here, and you have a photon coming. And this alpha is the absorption coefficient. So it's the integrated effect of that. Alright, so now this alpha is given. Now, of course, alpha will depend on the cross section of the particular process, which is through which this absorption is taking place. So this is given by h nu e, it's energy units, and it's normalized by 4 pi usually for, and then there is this function phi nu. This is of course a function of frequency. And then it's related to the populations and the two levels. So it's N0, where the two levels are 0 and 1. We have N0 and N1. So N0 B01 minus N1 B10. So I'm sure you are familiar with these. What are these B's? These are the Einstein coefficients. Basically, so this measures the number of transitions going from, so it's proportional to n0, and this is from n1 to n0 transition. So this is basically the net number. So that is what it is depending on. These are the Einstein's B coefficient. And what is this? This is something called a line profile function, which is essentially going to tell you what frequencies is this alpha sensitive to. Right, so alpha is a sensitive function of that frequency, which means it absorbs certain frequencies. I mean, it talks about absorption of certain frequency. So if this is a very peaked function like this, what it means that only for frequencies at that value and something close by will get absorbed. So this takes care of the band of frequencies and the distribution of and the relative weightage to those frequencies which is absorbed. So this has the full information as to what frequencies are selected. So this is like a frequency selection function or a line profile function. Now, so we have to do this integral basically over here to calculate tau, the optical depth. And see, here you have the populations of the two levels, n0 and n1. n1 is related to n0 by spin temperature, so n1 equals to n0 e to the power minus T star by Ts. And some G. G is 3 actually in this case. Triplet and a singlet state. Ratio of the degeneracies. Alright, so now what do you expect this phi nu to be? Now look at this now. This is the reason I'm doing this is because this is a very generic thing. This is not just for 21 centimeters. You could have any line frequency that you're interested in, and you want to see how the CMBR spectrum, how the CMBR gets, what is the optical depth for that particular. For example, you could, for example, choose Lyman alpha transition or something else, and you should be able to calculate this optical depth as photons pass through an IGM, through their gas. So, how is this? What is this phi nu? What is the simplest model, and what are we really talking about? We are saying that this photon is coming with some frequency. When is it going to get absorbed? At a gas at some redshift. It is going to get absorbed by a gas when it's at some redshift only when the frequency at the redshift of the gas is redshifted to the value which is 1420 megahertz there. Then only this gas will absorb it, right? That atom will absorb this photon only when its redshifted value matches the rest frequency of 21 centimeter emission. That's when it's going to absorb. So this you can clearly understand that you have to have this nu equals to nu 0 by 1 plus z, right? To have this, nu 0 is the emitted for 1420 megahertz. That's a known frequency. It will get absorbed. So this line profile function will only be non-zero for this condition to be valid. For anything else, this is 0. There is no absorption. So this takes care, as I said, it's a selection function. So clearly you can write this as in the simplest model as a Dirac delta. How do you write it? So you just say that this is basically nu 0 A. So you write this phi of nu as a Dirac delta nu by A minus nu 0. Right? So when nu by A equals to nu 0, this is non-zero. For anything which is, when nu by A is not equals to nu 0, this is 0. It's a very sharply peaked selection function. Usually there would be a spread. But I'm just modeling it by a simplest kind of a profile function where it's a peak. A sharp peak. So the moment the frequency, the redshifted frequency matches the 1420 megahertz after redshift, there is an absorption. So then you can just put this in here and integrate. So that is not difficult. And what we finally have is have to do this integral, you have to convert this dl first into frequency units for integration. So because alpha is a function of nu, you can always convert this length into a frequency unit. How can you do that? Just by noting that dr, which is now the cone wing radial distance, dr equals to some del r del nu d nu. So r, you have to express r as a function of nu. What does this mean? This radial distance to the cloud is a function of, now I call it function of frequency. What do I mean by it? So when I say r nu, it means we are not. So we have to convert, because this is the physical distance length. So first you have to convert it.
Along the line of sight.
Yes, it's along line. And you have to multiply by a to get dA. So a times dr equals to a. That's a physical radial length, right? But what does this r nu mean? R nu is the distance to a slice from where, if there is an emission, it would be seen at a frequency nu instead of mu emitted.
So you can relate it to the redshift.
Yeah. So basically everything. So finally you can relate it to redshift. So all these are equivalent ways of looking at distance. You can call it frequency. Since you have a reference line frequency now, you can calibrate your distances using that frequency. You can say that, okay, a distance r nu is the distance such that some nu0 is nu, is read as nu, is calibrated as nu after redshift. So nu, z, a, r, all are related by various conversions, and this is the conversion we shall be using here. So you just substitute, so you have this expression, you have nu by a, and you can integrate this out, the trivial integration, and you use this, and finally you have the expression for tau. Of course, you have to use the values of B01 and B10, which has the entire information about the transition. Right? So if B0, for various kind of line transitions, the corresponding Einstein coefficients will have the information about the strength of that particular transition. So that information is in B0. So finally, if you substitute all this, you will get this expression. So you will get this tau as 3, this 3 comes from this G, NH1, H, C square, A square by 32 pi H, AB, TS, mu E, and then you have del R, del nu, and yeah, it's A10. You can convert these B's to the A coefficient, because that is usually what is given in tables, and finally you have this. That's your expression. So if you can find this, you know tau. All right. So this, as I said, this is crucially sensitive to NH1, which is related to the ends, and you have this. So this is tau, and finally what you are measuring is Ts minus Pr times tau. So what you have is this. Okay. So finally you have this Tb given by that expression, and you can express all these in terms of omegas, this omega baryon and things like that. But that's not important. What is important that it is proportional to ns. All right. So what we are now stating is that if we now know the relationship of NH with my dark matter over density by some relationship, then we can use this to completely map out the universe by measuring this, and thereby know what the universe looks like at a given epoch. All right, by tuning various frequencies. The question is, how do we do that? Now, as I said, in the post-reionization epoch, when galaxies have formed and when the universe is largely ionized and only there are clouds of liquid hydrogen, there is a direct linear bias relationship. So actually, I'll show you this. Yeah. So this is at redshift Z2.5. And this is a simulation which actually simulates dark matter first. and it measures the power spectrum of dark matter, which is the lower thick curve. And then it also puts in the gas and looks at the power spectrum of the gas, and then it finds a ratio. So you can still clearly see that the gas power spectrum, which is the dotted line, is tracing the dark matter power spectrum till quite large values of K. Large values of K imply small scales. So only at very small scales you can see there is a departure taking place. Right? So this departure is only at very small scales. On large scales, the power spectra are basically related by a direct scale, and you can see this B square being now plotted as a function of K, and you can see that how it remains almost constant up to K equals 1. And then it of course starts growing. Those are the areas. So these are this part is where the linear bias model actually fails. You have bias B square because you are doing power spectrum. So you have two deltas, you have a B square. And in this region you can see this is failing. So this is for the forced reionization. A very similar holds at very early stages, redshift 200, redshift 100, way before reionization took place. There, both the deltas were much smaller than unity because the fluctuations have not grown. Right? So at very early universes, Z200 or Z100, which is where 21 centimeters is seen in absorption, that epoch, dark ages, there of course you can again expect a similar bias relationship. It's only in the intermediate phase transition during the epoch of reionization that such a simple picture does not hold. So this bias relationship, this picture of relating neutral hydrogen distribution to dark matter distribution by a simple bias, this is invalid when you are doing reionization. Why? Because neutral hydrogen is in form of patches. The neutral fraction is not a constant in time. The neutral function is a strange distribution in space as well because of these bubbles and coalescing bubbles. So you don't know what to do. So the only way to do reionization is either by doing full-fledged numerical simulations of those errors, or you can do some sort of semi-analytic treatment. But clearly this pure simple picture does not hold for reionization. That's something you have to keep in mind. So reionization is very tough because you have to put various inputs by hand and try to look at the picture. You just don't have a simple one-way simple theory. Okay, but if you're interested in the dark ages, I mean before reionization started and the post-reionization epoch, these are relatively simple when it comes to 21 centimeters, and measuring the power spectrum of dark matter is of course attainable by measuring the power spectrum of this TB. So this TB that we are looking at, if you measure the power spectrum of this quantity, then you are essentially measuring the power spectrum of dark matter multiplied by something. So you have a direct hold on the matter power spectrum. So has matter power spectrum been discussed? I mean, so everybody is familiar with this picture and how this comes to this form. Yes? Yes, no. No is good because I'll then discuss. No. Okay. So then you have to discuss. So finally, as I was talking last time, that you are interested in study of structure formation, and thereby you are interested in studying these deltas as they are growing. But as they are Gaussian random fields, it's no point taking one delta and looking at anything because the average is 0. So what you're interested in are the statistical correlations of these deltas, right? So we are interested in various correlations. So for 2-point correlation, 3-point correlation, 4-point. So in principle, I mean, for a general field, if you had all the correlation functions, then you know the entire statistical information, right? It turns out that if the field is Gaussian, then only its mean and its variance suffices, right? So beyond the 2-point correlation function, you really don't need anything. But if the field is non-Gaussian, then you would need the 3-point function, you need a 4-point function, and you have to go to higher functions as well, which has important properties of the field, right? So 2-point functions, of course, is very basic. We shall come to this figure and what we are trying to do here. So this is what people want to measure. And so on and so forth. These are the things which are interested in. Last time we discussed that this average that we are talking about, in principle, is an ensemble average, but we cannot do an ensemble average because we have only one universe. So what we replace this by is volume averages taken over different patches. Now here comes a very important question, that when you have only a small number of patches over which you can do this averaging, you are clearly going to get a bad representative sample. So there is going to be a noise, or rather a variance appearing by virtue of the fact that you don't have enough number of samples. And this is called something very important called caustic variance or sample variance. It's a fact that you are calculating these averages, but you don't have enough samples to do that, and that would introduce a noise, an error in whatever statistic you are trying to measure, and that is this. So what you would ideally need is a very large number of samples so that this is minimized. Right? So to have a very large number of these, you would have to look at different parts of the sky and you have to average, right? So to have a large number of such pairs, you would probably need a very large volume of the sky. Because you need a large volume of the sky, because then you can probably have many volumes on which you can calculate this and thereby take a good average. However, there is a restriction. For example, you are trying to measure something which itself is as a feature which is at very large scale. So for example, if you want to measure something, a fluctuation or something which is of very large scale, some large scale feature. So clearly your box has to be very big, because a feature, if you take a very small little patch, that feature won't even show up there, right? So you would need a large box, but your universe, at least your visible universe is finite, which means that if the box is large, then you cannot fit many boxes in there. So whenever you have measurements of very large scale features, you are liable to get lesser and lesser samples, because you have to take a large box, and thereby the number of boxes that fit inside your observation volume is going to be less. Whereas small scales, when you look at small scales, you don't have this issue at all, because you can take in principle smaller patches and you thereby have large number of samples. So cosmic variance is the prime source of error in observational cosmology when you're looking at large scale events. So if you want to measure some feature, cosmological feature, which is occurring at very large scales, the crucial source of error would be cosmic variance. For example, in the CMBR, if you look at the CMBR power spectrum, this low L, small l, which are very large scales on the sky, you will see there are enormous error bars. And those error bars are essentially because of cosmic variance, because you cannot have many samples of the CMBR sky when you are looking at scales which are that large. Okay, so that's one important point. So these are Gaussian random fields. When you do a Fourier transform and go into the Fourier space, then they are delta of k. Then they are delta of k, and the corresponding quantities is defined as a power spectrum. So this is the definition of the power spectrum. these quantities taken in Fourier space and then the ensemble average. Now, before going into power spectrum, a few important things about the correlation functions themselves. First of all, these are functions of position, whereas the correlation function can only depend on the difference of the coordinates, and not only the difference of the coordinate vectors, but the magnitude of the difference of the two vectors. Why is it so? It follows from basically translation on the invariance of this quantity, because you don't want this quantity to depend on R1 and R2. It has to depend on the R1 minus R2, which is going to make it translation in invariant, which is the statement of statistical homogeneity. Further, it can only depend on the magnitude of the difference of R1 and R2, which is statistical isotropy. So this depends if this is R1 and R2. This can depend on xi is depend only on R, where R is mod of R1 minus R2. So this is the correlation function, which only depends on the separation distance. What does this power spectrum measure? What is it? What does it physically quantify in terms of these fluctuations? What are these? These you understand. These are like the real fluctuations. What are these? You have resolved these fluctuations in Fourier space, which means these are like the normal modes, right? So you have a strange fluctuation. So let's look at it in one dimension. This is, say, some fluctuation in 1D. This is the delta as a function of x. When you do a Fourier transform, what do you get? You get a whole set of harmonics. What does it do? What information does each of these amplitudes contain? It says that, well, it's breaking up as if this fluctuation, this general fluctuation, which is like a random noise kind of thing, over a equivalent picture of a set of such numbers which are pure harmonics, which means they are all sinusoidals, right? So each of them have an associated scale k. Right? So what it does is, it's resolving this into a set of function, or rather a set of numbers, delta of k, where for each k, what it is measuring, it is how much of fluctuation is contained in various length scales. So by resolving this into its Fourier component, essentially means, like from here I can't say at what scale really do I have maximum power. If I look at this 1D field, you can see there is some oscillation which is roughly the wavelength is this. You can immediately say that this frequency is going to be the dominant frequency. Dominant k would be this length scale. You don't have a wave like this, which is a very large scale fluctuation. So by breaking the density fluctuations in Fourier modes, you're essentially trying to quantify as to how much power is there in the various length scales. And that is exactly what this, so that is in a mode, power spectrum measures the power by taking the square. That's why it's power, the square of the amplitude. So power spectrum P of k is a measure of what is the power contained at the scale k. So if you have, for example, two pictures, say two density fields, one has little spikes like this, and another field which has like, big mounds like this. Clearly you can say that if you calculate the power spectrum of this density field, it would have more power on small scales. Because you see on small scales, the fluctuations are there. Here the fluctuations are on a large scale. So the peak, the power spectrum here would have a peak at a small k value, because it's only at small k corresponds to large scales. So this is picking up more power at the larger scales, and this will have some peak at large k's or small scale. So k increasing is proportion is basically saying the scale we are probing is small. Okay. Now what about cosmological power spectrum? So cosmological density fluctuations, of course, have to be quantified by statistics, and power spectrum is a simple statistic, a two-point function in Fourier space. Now, the source of these fluctuations were at very early epoch, probably inflation. So inflation generated these fluctuations from some quantum fluctuations or something. So the power spectrum, which inflation provided us with, were something which just came from inflation by some mechanism, which, well, we have some ideas, but we are not sure as to what exactly gave a power spectrum. But as you know, Zeldovich gave this idea of this primordial power spectrum as being of a certain particular property. What is that? So Zeldovich said that the primordial fluctuations from early universe, that the density fields created by these primordial fluctuations were Gaussian, and they had a power spectrum which had a particular form. And Zeldovich made this remarkable postulate that it was just AK, some constant times K. That was the power spectrum. A is some constant. So what it says is that the power spectrum is what is called scale invariant. Now we have to understand what scale invariance means. A power spectrum of this form is called scale invariant. It's not that it does not depend on K. Of course, its power spectrum is K. But there is no characteristic scale. There is no K. This does not have any particular K to which this is there is some bias towards it. There is no additional affinity of this power spectrum for any particular K. It just scales everything. So multiply K by 2, every scale multiplies by 2, the power spectrum gets multiplied by 2. There is no specific scale in this particular power spectrum. So Zeldovich thought that that is the most reasonable thing to believe, that if inflation generates power spectrum, which is of this form, A of K. Alright, so if that be the case, and I plot P of K as a function of K, it will be this. Now, but every picture on every book would give you a power spectrum which does not look like that. There is a turnover, and power at very large scales, of course, falls down. So we have to understand this plot and thereby understand what is really going on. So what is causing that turnover in the power spectrum? Anybody has any idea? Vague idea? Okay, for that you have to understand this entire mechanism of structure formation. What is really happening? So see, there are, in very early universe was dominated by radiation. And radiation, of course, has pressure. Whereas, after the matter-radiation equality, matter started dominating, and universe was largely dominated by dark matter, which is pressureless. So there is pressureless matter dominating universe at a later stage, and whereas radiation, which of course mainly is 1/3 rho pressure for radiation, which was the dominating component of the universe at early epochs. Alright, so when there is structure which is forming, and this structure for formation of structure or growth of a set of primordials, so I say assume that I give some deltas to every point, and then just let them evolve. So what are the various conditions on which it will grow? What is it dictated by? The growth of fluctuations, physically. Gravity. First is of course gravity, and so your gravity will try to make this delta grow and form collapse structures, whereas the moment there is a collapse, pressure will try to sort of dismantle that collapse, right? So there are two opposing, especially at early universe, these two are clearly going to be competitive, right? Because there is gravity which is trying to collapse and radiation which is trying to throw it apart. So you have to consider the equilibrium between these two processes, right? And this is what was studied by genes. So you have studied these genes instability thing, right? So yeah, so that is precisely what is responsible for this shape. So what is genes instability? So you have two time scales. You have two time scales. One is the time scale which is involved with gravitational collapse. So what is that time scale going to relate to? To time gravity. This will be related to 1 by, as you can see, root g rho bar. You can see this has dimensions of time. Just check. So this time scale is going to be related to gravitational collapse. I mean, pure gravity, that order of time that it takes for things to collapse. And then, if you have a medium through which there is some sort of a pressure wave. Now, sound waves are nothing but pressure waves. So, unless there is a pressure, you can't expect there's going to be sound wave. Finally, sound wave is like propagation of a diffraction and compression, right? So, which is essentially pressure wave. So, if you have pressure in the medium, then you have another time scale, which is time scale of the pressure causing, and that would be given by some characteristic length and Cs, where this is the speed of sound in that medium. Right? So these are the two time scales which are competing when you are forming structure of some size r. So there is this time scale, and let's assume there is a background density. So we are doing an order of magnitude calculation. So depending on which is greater, you would either have structures collapse, or you would have, the pressure will dominate. So, and this is given by, so the relationship is basically now stated in terms of what is called a Jeans length. So, for example, if 1 by G rho, this is less than R by Cs. What does this mean? It means that this time scale is much smaller as compared to this, which means this is a slow process, and this is happening much faster. So which means collapse will occur, because this is so slow that this doesn't care. So this is happening faster, and it's really happening. Whereas this is like taking forever. Whereas if you reverse it, pressure processes will annul the whole thing, and this will not even take time to collapse. So this can be reworded as R greater than some Cs by rho d rho. This is the condition when collapse is going to occur. So there exists a scale which is now related to the sound speed and G and rho bar and things like that of that particular medium. And for scales which are larger than that, there is a collapse. So when you're looking at scales which are larger than that, those scales would collapse. Whereas for scales which are smaller than that, you won't have this. So to have collapse or formation of collapse structures, or in other words, for a growth of density perturbation, you need to have scales which are larger than something called the Jeans length. So when the scale is greater than the Jeans length, you have a collapse. Now in the radiation dominated epoch, and this is exactly what is happening over here. So what marks a transition in that curve is essentially a transition between radiation dominated epoch and matter dominated epoch. So let's just see how it works. So let's state that Zeldovich has given me this AK power spectrum at some t, some early universe. And we are just looking at the evolution of this power spectrum as time goes on. So at this early universe, when this is the power spectrum, you clearly have radiation, nothing else. Right? And you have to also understand it is not only this radiation, pressure gravity interaction, the universe is also expanding. This analysis has to be done in an expanding universe. So when the universe is expanding, what happens is there are larger modes. So let's say there's a mode, which is large K. So what happens is there would be modes which were outside the horizon of the universe. The universe is expanding, and which keeps entering the horizon as the universe expands. See, when you say K, it ranges from -0 to infinity, all possibilities. But all those modes most of them are outside the horizon because the universe is small, very small. So the universe is small. Certain modes, which are of course, the universe is small, K, the scales of course we are talking about are the large scales. Right? So K is large, so somewhere here. So as the universe expands, and K goes this way, right? Because the universe is expanding, and the corresponding scales, the length scales are increasing, thereby K is decreasing in this way. So we're looking at this as a series of snapshots, power spectrum at different epochs. So when universe is expanding, modes which are large, so certain modes are constantly entering the horizon looking here. The modes which are outside the horizon in the radiation dominated epoch are of course larger than the Hubble's the gene's length because they are large scales, and those are the ones which would be growing. But the moment universe is expanding and a mode has entered into the gene scale, into the gene's length, that growth is suppressed. So a mode expands only when it's outside, when it's larger than the gene scale. Now in the radiation dominated epoch, you can see actually that the horizon is essentially the gene scale, length scale. So the moment a mode enters the horizon, its growth is suppressed. So as the universe evolves through the radiation dominated epoch, so at the next stage, it is not like all of them have grown like this. A mode which just entered will actually get like this. Its growth is suppressed. At the next instant of time, this is of course suppressed, even this will be suppressed. This has further suppressed. And this suppression of modes keeps going on till a point where there is matter, this radiation matter equality occurs, and after that, since it's all matter, there is no pressure at all, so all the modes are growing. So this suppression of growth of certain modes occur because there are certain modes which are entering the horizon as the universe is expanding, and this horizon is basically size is essentially closely related to the gene scale in the radiation dominated epoch, and thereby as soon as a mode enters the horizon, its growth is suppressed. So after some time this will be like this, and this finally takes this form, and this corresponds to the time where the mode that is just entered is at the matter radiation equality. After this, the shape does not change. After this, all modes are going to grow. The shape will remain the same. So everything, this entire thing will just get shifted. So imagine this line as if you start with a power spectrum which is like a line, AK, and it's sort of pushed up because everything is growing, except as an evolution, there are certain modes which are not growing as much, it's suppressed, and thereby someone is pulling these down. And till how much will occur? It will occur at the K, till the K, the suppression. That K corresponds to, so K eta, K equality eta equals to 1, where this eta is the matter radiation equality. So that is this K.
When you say suppressed, does it mean that they are growing at a slow rate, or does it mean that
Slows down.
has overtaken the...
No, so the modes which are outside are growing. Where this growth is not, that particular mode is not growing anymore.
So it's not growing at all.
Yeah.
It's not that it's growing at a slow rate.
No, but that is at 1K. So the next moment another K enters, and now that stays there. It's no longer growing. So as if this stays here, its friends earlier have all gone up. So it's like somebody has stuck it there. So this mode, which corresponds to this line over here, this remains here. Whereas at the next time, this has gone all the way here, and now this fellow, this is stuck here. So it does not grow anymore. So it keeps, at each stage of a mode entering, that particular mode does not grow. So that's why it keeps bending there. And everything starts growing only after. So this plot is basically the power spectrum today, the present day power spectrum. So the primordial power spectrum is this, and this is what is called the present day power spectrum.
There would have been modes in the early universe which were already within the horizon.
So we assume that the early universe was very, very small. So very, very small. So that's
But still limited.
so most modes are outside.
But there would be a non-limited modes with
Well,
lines.
Yeah. So that's why that's why PK does not go to 0. I mean, so that's this point, right? That's this point.
Yeah, that's that one. So, but in the early universe, we assume it to be linear.
No. That is what. So that is given. So we don't know what gave this. So that's why I said inflation is believed to have given this at that point. So once you have inflation is over, and now your Hubble expansion starts. This is purely Hubble expansion. What we're not looking at inflationary expansion. So inflation is over, and you are given this power spectrum. Now you start your analysis. So we are not going beyond that epoch.
But then after inflation, it would make more sense to have more number of modes which are within the horizon than outside.
Yeah, but that's the starting point. We are starting with the power. We don't know what the power spectrum was before inflation.
Yeah, I don't know.
Right. But that is it. This is the shape of the power spectrum at inflation, and universe is still small compared to our universe today. Right. So that's what we are comparing with. So from here onwards, we look. And that's where radiation epoch starts. This entire genes instability and growth of structures. So before that, yeah, we don't know. So that's why this is like an initial condition. So we start from here, as if this is given, and that we call now as some t equals to 0 in some units, and then we just see how that power spectrum shape evolves through that.
And so at that t equals 0, we would have some modes.
Yeah, but we are only comparing.
Which wouldn't have grown.
Yeah.
So they would already have been.
Yeah, but grown is like we are growing from there.
Yeah, from what we
Isn't-
got after.
So we have that, and growth or suppression is only from after that. So this is at the exit of inflation, and we could have some. Of course, universe of finite size, so there are some modes inside the horizon, of course. But we are interested in modes evolution after this. Alright, so this is the thing. Of course, now it turns out that this is, of course, if the universe was only cold dark matter. So this is how it would look. And we should now see that actually this power spectrum is even more interesting. It has oscillations, which is actually what you observe in CMBR. The CMBR power spectrum has oscillatory feature, right? So where does these oscillations come from now? So you have to understand that as well. So this is just the power spectrum and the matter power spectrum, and we don't have any oscillations as if, at least at this stage of analysis. We actually do see small oscillations in this part, and you have to understand what is the cause of that. Of course, this corresponds to, now look at the scales. Now, if you actually plot this is something which is you have to understand, that if you look at these scales, these are extremely large scales, whereas these are extremely small scales. This scale corresponds to an epoch of matter radiation equality. So most of our observations in galaxy, observations in 21 centimeters, we are interested in this region. So going to scales larger than this, you have to go to, see, redshift 3.5. So at redshift 3.5, you need to have an L. So L equals to 10 corresponds to this scale. That's a very large angular scale. So you have to cover large parts of the sky to probe these areas, and you have to go deep down in redshift because you need that volume, right, to probe these scales. So this is very important, this plot, because you have to understand how far you can go down in redshift and what kind of scales you probe at a given redshift. So your telescope has to observe a certain part of the sky. The telescope probes a certain part of the sky, and thereby it can only probe a certain maximum scale. If the telescope has a beam which observes a certain part of the sky, all right, it can only have probe a maximum scale of that size, right? So it cannot cover anything outside. Even that scale would be very bad because it will have only 1 or 2 realizations. So the cosmic variance would be very large. But at least that scale, that's a maximum scale it can probe, and thereby it can only go to a minimum value of k. Any observation has a minimum k, which is related to the maximum scale it can see on the sky, and a larger scale, k, which corresponds to the resolution of that instrument, the smallest scale it can see. Every observation has a range of k values that it probes. And that's true for radio observations, galaxies, anything, CMBR, whatever. You will have a k min and a k max for an observation. And 21 centimeter observations are here for all ground-based telescopes with reasonable frequency. Alright, now coming to the next thing that I was wanted to say is this oscillation which occurs in our spectrum. And so where does that come from? So to understand that, so of course you can do the maths. It will take 1 or 2 days of coupled radiation, baryon, photons, fluid dynamics. But we can still understand the origin of these oscillations from a very nice physical argument. So let's assume that this is the scenario. So you have, say, we're looking at everything in, say, in configuration space and in position space, and this position space is one dimension. This just have one dimension, say, and I call it R. And let's assume that you give at some R equals to some R0 or some origin, some pulse, some overdensity. Just assume how, so let's just try to understand how these overdensities behave with time. So we give some overdensity and say it's a peak. Actually, the mathematics of this is actually there. It's basically what is called Green's function techniques, where you give a pulse, a Dirac delta source, and you study the response. But we shall do it pictorially without going into the maths. So what you do is you give a pulse or a spike in your overdensity, and you are plotting delta E. And what delta is it? It's delta of radiation and of dark matter. And of course of baryons, everything. So I give a pulse to all of these quantities and they have a spike there. Now we are relaxing the system and we want to see what happens to this overdensity created at some point. So what do you expect? Now dark matters of course don't interact with photons, so that spike will stay there and gradually decay away. Whereas photons coupled with the baryons will have a sound speed, effective sound speed, and that plasma, but then it will take that pulse away from that center, right? So after this is some t equals to 0. After some time, what you expect is a situation something like this. The dark matter part has sort of mellowed down, it has flattened out. So this is dark matter. Whereas the photons plus baryons, this tightly coupled plasma, this has gone out radially to some distance.
What is this free electrons?
Yeah. So we are believing that they are tightly coupled through Thomson scattering, and the photon is just dragging the baryon along with it. All right, they are not allowing the baryons to stay away. Through scattering, this is behaving like a single fluid, and it's being pushed out with a sound speed. So the velocity by which this comes here is the velocity of sound in that matter. So you have del rho del p, c square, right? So that is what is happening. Now, after some time, what do you expect? This will keep moving, right? How long will this keep moving? It will keep moving till the epoch comes when the photons will dump the baryons after it decouples. So after that epoch, photons will say, well, our friendship is over, I'm going to free stream from here. So baryons are dumped there. And the photon still goes from there, right, off. So that photon densities will just disperse off, slowly it will go off to 0 because it will just move away. Whereas the baryons now, so I will look at this further, so this has now flattened out, initial dark matter over density, and there comes a stage where this is baryons and photons have gone away. And this corresponds to RS, which I call from Big Bang to the radius of the last scattering circle. So now baryons are sitting here. This has more or less flattened out, but this now is at a higher peak because this was so sharp and was carried by the photon. So what it will do now, it will draw some matter from here, and this will probably grow a bit, but what essentially would mean that this will more or less flatten out. And you'll have a peak there. Now see, this is delta of R as a function of R that we are plotting, right? This is the scenario. So if I look at it in a 2D thing, there is this little peak here, and there is a ring of. So this has gone after some time. This will be if you look at a 3D simulation, you could have seen that this would have just gone low, and you have a little ring of matter forming an overdensity at Rs, which is equals to Cs Ts, the velocity of sound and the time it hit the edge of the universe at decoupling. Now, you have got it, because see, the moment you have this picture, and this is exactly what is happening everywhere now. So you have various deltas which are nothing like the pulses, and finally they are just forming these shifted, so they have these fluctuations forming at the last scattering surface. Now see, the moment you have this, and you want to look at it in Fourier space, you will see it immediately leads to oscillation. So how do you do that? See, if you have a shifted peak in a function, what does it Fourier transform look like? So you can just think of this as a Dirac delta. So delta R minus A. This is like some delta Dirac R minus some Rs. What is the Fourier transform of this quantity? You have to just multiply by e to the power I k r and integrate, right, over dr. Right? So it is e to the power I k r s, which is nothing but an oscillation, but the wavelength of that oscillation is Rs in k space. In k space, this is nothing but an oscillation with lambda, which is now Rs. So that's why this oscillation. So delta, if you look now, delta of k, this is an oscillation, so let me plot it nicely. In that same picture, if I plot delta of k now, it's going to be an oscillation, and this is the radius Rs in k space. And of course, the square of this will be the power spectrum. So the power spectrum, in the power spectrum, you expect an oscillatory feature, and the oscillatory feature has a characteristic length scale, namely the wavelength of that oscillation, which is nothing but the sound horizon. We call it the sound horizon at decoupling. So what you have actually is this power spectrum, but you have oscillations here. And the wavelength of oscillations that you have over here is nothing but this Rs, which is very, very important. Why? Because we now have in our power spectrum two characteristic length scales. One is of course this, but you also have this scale. You have another scale in your power spectrum. And you have a length scale which is now so properly calibrated. It is such a beautiful standard ruler. Like a standard candle for supernovae, which are objects of known flux, known luminosity, you now have an object, namely a feature in your power spectrum itself, which is of a known length, right? Which is nothing but the sound horizon at matter radiation equality. Sorry, not matter radiation equality, decoupling. Sorry, decoupling. This is matter radiation equality. So, what is the use of this? The use of is this: if you have measured this feature, this Rs feature, in some measurement of power spectrum, right, at some other redshift. So this is now a characteristic length which is on the CMPR, or on the last scattering. This is the length of the last scattering surface. But this is also a feature in the power spectrum, which would, manifest itself. So if you have, say, for example, measured a length scale So you probably know this. There are two methods, right? There is the idea of a standard candle and a standard ruler. So what is a standard ruler? What is a standard candle? You have luminosity of something which you know, and you have an apparent luminosity which you measure, and you measure the distance, and then your distance is a function of all the cosmological parameters, and you can measure those cosmological parameters. In the same way, you can measure angular diameter distance, dA, by finding the feature of something which subtends an angle theta. So you have some length scale that you have measured, and you find that angular diameter distance as a function of theta. This is measured. Now, the feature that you have measured appears to you, of course, if you have some standard length and you observe it here, you observe it here, you observe it here, they will subtend different angles, right? But the length is the same. So, and now, reversing this argument, you can say that if you know the length of the absolute length of that object and you have measured the angular diameter, angular angle that it subtends, then you can measure d as a function of z. Right? So this is what people do. People look for the oscillation feature in their observations and they look at what angle we are getting it. And thereby they measure the corresponding angular diameter distance, which they can now measure as a function of redshift, and again thereby constrain cosmology. So that is the method of standard candles, and so this oscillation is basically called BAO, baryon acoustic oscillation. So the BAO feature, if you can measure in any cosmological observation, in measurement of any power spectra, then you can say that, okay, so I can calculate dA at that particular redshift, and d as a function of redshift, if you know, you can basically do cosmology. So we want to find dA as a function of z, angular diameter distance as a function of z. But this is observing that particular feature on the transverse direction, on the transverse sky. So you can also find this length. See, when you measure the 3D power spectrum, this is, I did the analysis in 1D, but you finally measure the 3-dimensional power spectrum of the entire field. And this feature would also manifest itself as a radial feature. You also have a radial feature. So if you can measure the radial feature, measure the imprint of this standard ruler in the radial direction, so there you will calibrate not using dA but h of z, which is of course measuring distance in the radial direction. So there you can measure h of z. So these are very useful. So it is believed that in 21 centimeters. So now this is a very important thing to note, that it's very tough. Why? Because see, these are the scales where you are probing it. And you need very large volumes because this oscillation is approximately known to be a few percent effect. So if you have a power spectrum, say this is the without the oscillation power spectrum, and then you have an oscillation riding on it, this in itself is of order of few percent. So you have very small little fluctuations, on a small little oscillations on top of this. So you need to measure these at very, very small error bars to actually detect the feature, and it has been now confirmed that this is being observed in galaxy surveys. But of course, if you do the same thing for 21 centimeter power spectrum, so what you do is you measure the 21 centimeter power spectrum, which will be proportional to this power spectrum, and thereby have exactly the same features. So you will have the same features, and here the advantages are, one, you can probe extreme large scales, extreme large case, extreme small scales, which for example you cannot do using either CMBR or with galaxies. With CMBR there are a lot of systematics, and of course there is also a rapid suppression of power at large Ls. See, what is this L? There's an L and a K. L is basically the projection of the 3D onto a sky. So L is this angular. It's the Fourier L and theta, K and R. What K corresponds to R is what L corresponds to theta. It's a Fourier conjugate of the angular variable on the sky. Right, so this is basically when you look at the angular power spectrum. But essentially you can show that L by R is what is related to K. It's under some approximations, of course. So R is the radial distance to the surface on which you are looking. So CMBR, of course, people look at the sky, so thereby they have the L. So at very large L's or very small scales, there is a suppression of power. And this suppression of powers comes because of some diffusion and something called silk damping. So there is some processes which makes the power abruptly go low at large L's. And that problem is not there in 21 centimeters, so you can actually probe to very large Ks. More importantly, since you have a volume to probe, since you are now interested not only in a surface of the sky, but you have a cube. Your data, so here is your observer, and you have and this is some Z, this is some Z prime, and you have this entire range of redshifts to probe. You essentially have a full volume instead of a surface. So number of modes at which you can measure the power spectrum is much, much, much higher. Because see, on a surface, you can only have certain Ks, right? But when you have volume, you have many, many more modes because you have an extra degree of freedom. So the number of modes are much higher, and thereby, so there's this plot I made. Yeah, this. So we are comparing here CMBR with 21 centimeters. You can see, so we are only considering a small redshift bin, I mean not even a large redshift range. Redshift is 2.5 to 3 basically. So assume that there is a 21 centimeter observation which has 0.65. 0.65 is a fraction of the sky that we are observing. So it's half, approximately more than half the sky. And we are probing the entire redshift range, say 2 to 2.5 to 3. We can clearly see that an N denotes the number of modes that are accessible at a given K. So, and you can see that clearly is very, very, very large, much larger. You know, it's almost, you could have plotted it in log scale also. So it grows so much more as compared to the CMBR, especially when K is large, in small scales. So in small scales, you clearly have a very big advantage using 21 centimeters. First, because you don't have the silk damping, suppression of power, and your availability of a large number of modes. So next generation cosmology, CMBR, people know what to do with CMBR now. So 21 centimeters, people have still not detected cosmological signal. I mean, forget about doing cosmology, this is all theoretical in the sense that people are of course trying, there are these telescopes. But why has it not been detected? The main issue in doing this detection is, at least based on Earth, is the fact that the signal is extremely weak and our galaxy has enormous amount of contaminants. So the signal that you want to observe is 5 orders less than the contaminants. So the foregrounds, as we say, of 21 centimeters, they are like 5 times greater. So how to eliminate these foregrounds and how to finally scoop out the cosmological signal. So there are various methods being proposed and people are trying to work on this, but probably SCA, Square Kilometer Array, which is like the next generation telescope, is completely dedicated to cosmology with 21 centimeters, and there's this low frequency LOFAR and MWA. So there are various telescopes, including our own GMRT and OT radio telescope. So there, but you need thousands of hours of observation time, and you need dedicated telescopes to reach a sensitivity level where you can throw away the foregrounds and get out the cosmological signal, and thereby, first of all, okay, so first of all you have to get the signal, and then of course you can do a full look at it in various scales, which is like even more tougher. Then you can actually do a Fourier transform and thereby measure power spectrum. So measurement power spectrum will come at a much later stage. First of all, you need the background. Like in CMBR, they first discovered the 2.7 Kelvin, which is T0. So here you need to calculate the background first, and then the inhomogenities, and thereby power spectrum. So it's a long way to go, but it's believed to be now the most promising field because of obvious reasons. And you are basically mapping out the entire universe over a huge redshift range. So yeah, so I think that's all I have. I could have gone on various other topics, but there's no point talking about details and technicalities of radio observations. There are lots of observational issues when it comes to detecting 21 centimeters. But yeah, so we will take questions instead. people believe is that most probably because of the foregrounds, this would be detected for the first time in cross correlations. So you would have another field, say CMBR or galaxies, which you cross correlate with your 21 centimeter observations. Only and both of these are say tracers, so they would both be proportional to the the dark matter over density, and thereby the part which is the foreground won't correlate and would appear just as a noise. So in the main signal, you would only have the pure signal. See, the problem is when you do autocorrelation, we don't even know whether there is a signal or whether it's just foreground. So when you cross correlate, you know that only the signal part will correlate. So what you are getting is actually the signal, and the rest of it is noise. So you know that there is a noise and but here when you are just doing autocorrelation, you are clueless what you get. So even if you get something, you don't know whether it's foreground or not. Even when you have reduced all your noise levels and your foreground subtraction, everything is done, you still can't be certain that this is your signal. Whereas in cross correlation, if you have reduced your noise levels and you have subtracted your foregrounds, the remnant, you have theoretical reason to believe that that is a signal, because only the signals would correlate. So that's why people believe that at least the first time the detection would be of the power spectrum or even the signal in cross correlations with other tracers. And yeah, so we have any feature that you can see imprinted in the matter power spectrum, as I said, would also get imprinted in the 21 centimeter power spectrum. But here we are doing a tomographic imaging, and the observations are radio observations. So that has its own advantages.